Howdy, everybody. Today was a bit of a weird day. I didn't really find a great way to record my solution, um, but I'm at my desk now, and I thought I'd just take some time to describe my solution. I think, like a lot of people looking at other people's solutions, there was there were some tricks that made it a little hard to solve. But anyway, I thought we'd just go through it. I also only solved it in Rust today, so I apologize if you're looking for the Haskell solution. Um, I think my goal right now is I'm going to try and stay up to date with the days and then come back with other videos as I have time to do them in Haskell. So I still want to learn Haskell. I got some cool feedback from people on some of the message boards about using Parsec for parsing in Haskell. So I did make those changes in day 2. Maybe I can just show those to you really quick. But then we'll go over day 3 in my solutions. So let's just do that right now. Let me go back to day 2, and here's how it changed. So if you remember, I was doing a lot of just like trying to do my own matches and trying to parse out little chunks at a time. It turns out that if you use this Parsec utility, or this package module, I guess is what it's called in Haskell, you can have it do stuff for you. So for example, when I'm trying to parse the colors, just as a refresher, if we look at the input, we'll have these chunks from like here to here where we say, oh, there were 19 blue and 12 red within a single round of him pulling out the numbers. What I was doing is splitting them and then doing some stuff on my own. Instead, if I use the Parsec utility over here on the left, you can see what I can do is just call these functions saying, hey, I want you to, it's using monads to do this, right? So I can say, hey, I want you to parse many1, or I want you to do many1 of digits, and that will become the count. And then there should be some number of spaces. And then I want you to do many1 of letters, and that will be the color. And then I can just return the count as an integer and the color. So you can then chain these things together. So when, for example, I want to do an entire round, right here, when I say parse round, I can now say I want to do a bunch of color parses using the separated by a string, comma, space, right? So now what it's doing is it's going to take this, and it's presumably I'll have this entire chunk, and Parsec will recognize that, oh, I can split this right here, and now I have 2 of those, and for each of those I can call parse color on them. This one was still, I don't know that it was fewer lines of code, but it's because the input was relatively simple. I can imagine on like more complex ones it will be more helpful. It didn't actually help with day 3 because day 3 was just a grid system. But anyway, so I still had to use this color find thing. I'm really interested, if you're familiar with Haskell, how you would have done this differently. But like the idea is I'm parsing all these colors, and I want to put them in either the red, green, or blue right here of my data structure. And so I still had to do this color find thing where I say, hey, filter on all of the colors, and the one that matches will be the color that I put in the round for red. So you can see here, I still return a round where I call those color finds. I don't know. It seemed okay to me, but there might even be a better way to do that with Parsec. I only had like a half an hour to read some tutorials on Parsec and then try and implement this, so it may not be the optimal way. But then again, you can keep layering and chaining these things, right? So now that I have a round, which is like this part right here, a game is really just multiple of those rounds separated by a semicolon, and then it has the actual string literal game right here, followed by the game ID. So you can see I can do a parse game here where I say, hey, I'm looking for the string game, and then I'm looking for many one digits, so at least one or more digits, and that will be the ID. And then I'm going to look for the actual string colon space, and then I want to, the rest of it can be parsed by parsing the rounds, which are separated by a semicolon and a space. So I use the parsec set by, and then I parse each of those rounds. And then I can return a game with those rounds and the game ID. And then, instead of having to do it line by line, I can get the parsec to do that as well. So I can create a list of games where I end by the ends, right? The new lines. So you can think about this as like essentially calling lines and then parse game on each of the lines. Anyway, there's multiple ways to do it, just like any other language. I thought I'd try and do it in Parsec, and this is at least what I got, what it would look like in Parsec. So once you have the games, the logic doesn't change that much, right? When you're calculating, like, is it a valid game, you're just going to go through all the rounds and make sure that they meet the criteria. And then when you're calculating the power of each round, again, you're just going to get the maximum of the reds, the maximum of the greens, and the maximum of the blues, and multiply them together and get it. So like this code doesn't change, but that parsing part does change using the parsec. Anyway, it's a pretty cool utility. It actually made me interested to see if there was something similar like this in Rust or Go, which are the languages I use most often. Rust has Serda, or however you say it, Serda, right? And that's really good at like doing structured parsing. I imagine you could probably create a Serda parser for this thing. That might be a cool thing to do after the fact and see if we can get it working. Obviously, they have libraries like, if you want to do JSON, which I'm most common with, like, for example, in Go, you can just use encoding JSON. I assume Haskell has things like that as well. But it's kind of cool that it has this generic parser where you tell it what it should be. And I'm curious how you would do that in Rust or in Go. Maybe you kind of define your own using, again, something like Serda or not. Anyway, this is my change solution. Maybe I'll put this in here, put this updated solution in a gist with this video so you can see it. That being said, let's go to day 3. So because we're doing an overview, I'll just leave you a link and you can read it. But the gist of it is you have you're trying to fix a gondola that you need to get up to the water source. And you're given this grid style input, and the idea is, can you find the pieces or the numbers within here that are next to a symbol, including diagonal, right? So in this case, 114, the dots aren't considered a symbol. For 114, notice how if you trace around it, you don't get any symbols. For 467, you do. This asterisk is diagonal to the 7, so it does get counted. And what it wants you to do is like the sum of those, right? So in this case, 114 is not one and 58 is not one, but all the other ones are slightly adjacent. So my initial thought, and what I ended up going out with, was just treat this as a grid. Look for a digit and then see if you can find an adjacent asterisk to it. The one gotcha was you do it recursively. So this is a whole number. I would find this digit and I would look for its adjacents, and it wouldn't have any adjacents, but it would have an adjacent digit to the right of it, directly to the right. And so I would recursively then check if this one was a digit, and then I would recursively check if this one, was adjacent. And eventually I would find it, and so that would mean the whole thing was adjacent. And then I just have to find this whole number and add that to my sum. So what does that look like in code for part 1? You can see here, just doing standard input parsing to get my grid system. I think I call it map throughout the rest of this thing, the map, because they call it a map? Maybe I need to change that, but I think they call it a map of this, or they call it a schematic, right? So anyway, I basically just loop through it and I say, hey, if at my current position, am I an ASCII digit? Is it adjacent? And if it is, then I want to find the whole adjacent number to it and add that to my part 1 solution. The one gotcha is that I needed to, for this whole number function, is if the number was more than 1 digit, obviously I'd want to increment y by however long that number was. So if you go back to the example here, this returns true in the adjacent to symbol function. It says, yes, that is adjacent to a symbol. So I have this whole number, 467, which this whole number calculates. But now I want to jump past this 7, so I don't also find 67 and 7 as I'm iterating through it, right? That would give me the incorrect results. So what do I do there is I not only do I pass the number, I also pass the length of the number, and then I increment y there. So this is basically just a simple loop with that gotcha, with that special case of, hey, when I find a number that has a symbol adjacent to it, I want to add that whole number to my solution and then increment my y to compensate for that number. So what do these two look like? I wrote a couple helper functions. I use this adjacent function to say, hey, at any coordinate in the schematic, can I give me an adjacency list of all the things? It's a graph, right? We are using an array for the graph, or a matrix for the graph, but we do want to calculate the adjacency list of that thing, and it just happens to be all of them that are on the diagonal, all of them that are up, down, left, right, and diagonal, right? The one thing is, obviously we don't want to go off the edge on either direction, so you can use this saturating sub. I think I learned about this when I was practicing some other programs earlier this year. The saturating sub is a cool function where it says, hey, subtract this number by 1, but don't let it underflow. Don't let it go under 0, because we're using u sizes here for the array indexes. And so we don't want it to become -1. So we use the saturating sub, which says I'm going to stop at 0 if it happens to get there. And the same thing if we go overboard, right? So we say, hey, if I want to pick the smallest number of x plus 2 or the max x, which is in this case is 140. But the idea being, I don't want to go off this side of the array either. I don't want an adjacent number I don't want to produce an adjacency coordinate that has 140 or greater. And that's what this little trick here does with the max, the min of max x and x plus 2. Same thing with the y's. So then I just iterate through those, and I say if x and y are equal, I'm at the origin of my adjacency list. I don't want to include that one. Otherwise, I push the rest as long as they're within the grid. So given that, the adjacent to symbol function is pretty simple. I just call, for each of the adjacent cells, I can go see if that adjacent cell is not a digit and not a dot. And if it's not, then I return true. And then here's this special case where I say, oh, but if this adjacent one happens to be the one directly to the right of it, then I also want, and it is a digit as well, I want to call the adjacent to symbol. I want to recursively call this function on it. So now I can check and see if it's one. And if it happens to be, then I return true. If this fails, one of my early iterations, I just returned the result of the adjacent symbol. If this fails, I still want to keep checking, right? Because there may be more items in my adjacency list. So I only return true if it's found, and I only return false if like both of these always return false or don't return true, then I want to return false here. Anyway, that's all to say now I have like this program where I'll go through each of the items one by one. And as I find one, I check to see if there's anything adjacent to it. And I can do that recursively for each of the numbers that would be included in that digit, right? So now that I can find the valid ones, I want to ask myself, what is the whole number? What is that whole number that is included in that position at XY? And that's what this function is. It turned out not to be too tough, but it was a gotcha that had me going for a little while, which I'll talk about in a second. The idea is basically starting at the whole number. I know the numbers will only go left to right, so I can just start incrementing the Y position. And I actually think if you're thinking about X, Y's in like a graph in mathematics, I have them reversed. I always hate that, how we do that in programming. Anyway, but the idea is I know I'm always going this way. And so I just keep incrementing it as long as it's a digit, right? So the one bounds check you have to do, though, is you have to say, hey, is as I'm moving, I don't want to move out of bounds right here, right? And the gotcha that I had was I did this bounds check after this right here. And so I kept, obviously that produces a stack trace, right? I get an overflow exception. And then my initial thought was, oh, I'm just doing some off by one thing. And so I just did map lane -1, which was actually not correct. And what that caused me to do is, if you look in the input of the thing, it's this line right here, like the 55th line, at least for me. Notice this one is a 100, and it happens to be associated with this asterisk right here. If I shrink it down, you can see they line up. But I know it's a little bit hard to see when it's that small. But the idea is this 100 is 1, but it was only counting it as 10 because I wasn't including the 0. And so the fix for that was to check this first and not do a -1 because it wasn't including that -1. Or I wanted to go up to the end of the map, not one less than it. Anyway, it was a weird bug. It shouldn't have been a bug. You always bounds check first, right? Anyway, once you have your Y position, which is the beginning of the number, and now you have your J position, which is the end, you can just collect that as a string and turn it into a usize. This seemed like the easiest way to do it in, quote unquote, one line. But you could potentially do something where you said like, if Y minus J is 3, I can do the parsing myself, right? You can do like the first number times 100, the second number times 10, and the third number times 1, something along those lines. Or even do like maybe some bit shifting. But this seemed good enough, and I didn't feel like the need to like optimize it in that kind of way. And then, okay, so once you've got, that's the actual number, now I want to return the size of the number, which is just J minus Y. The idea being now I can skip ahead. So I think that was it for part 1, right? Again, to recap, we just check if we ever find a digit, and if we do, we see if it's adjacent to a symbol recursively, like would any of it or the total number's digit be adjacent to it. And then if it is, we calculate the whole number and do that. Now that I'm thinking about it, you could rearrange this slightly. You could say, like, if it's a digit, get the whole number, and then you could iterate over all of them and just see if they're adjacent. And if any of them are, then you do this. That would be another way to do this. Then you don't have to do it recursively. The numbers are small, so the recursion I don't think isn't going to matter in the end. But that's a potential way to also solve this. Okay, so that was my solution for day 1. day, or sorry, part one of day three. Part two, like what happens is you realize the engine isn't actually moving, and it's because of some of the gear ratios, and so you need to figure out what the correct gear ratio is. And so he wants you to give you a list of he wants you to give you the sum of the gear ratios, and the way you find the gear ratios is through the asterisk. So any place you see an asterisk where there's exactly two numbers connected to it, so you notice here's an asterisk in a 467 and a 35, this gear ratio then is the product of those two numbers, and he wants you to sum up all of those. So this is a gear, these two make a gear ratio, you multiply those and add that to the sum for part two. Notice this one is not, because it only has one number associated with it. This one is because it has two, so you multiply those two together, add that to your sum, and you get your gear ratio. So how does this differ from part two? There were a lot of, or sorry, from part one. I think there was, obviously, at least in my mind, the way to solve this was to just now go find all the asterisks in the thing and see how many adjacent numbers there are. And if there's exactly two, multiply them and add them. And so you actually see that's my solution to part two, is I just literally go through the whole grid or the map and I say, hey, is it an asterisk? If it is, find all the adjacent numbers, and if it's equal to 2, multiply them together. The trick is, what are the adjacent numbers? Now, we can reuse some things, right, from part 1. Obviously, the adjacent function we can reuse, right, because we want to find those adjacent things. We don't care about the adjacent to symbol anymore because it's not a... we're not looking for symbols. We're looking for numbers now. The whole numbers is still useful because once we find a number that's surrounding it, we want to get the whole number. And so I can kind of show you what my thinking was right here really quick. The idea that I had was check the left, right, top down for numbers. Check all of them for numbers, and if any of them are, just find the whole number. So use that whole number function to finish it for us. And then that would solve it. The one got you though is it doesn't show it here, but imagine this is like a 1, for example. The whole bottom is a 1, and so if you've checked the whole bottom, if it happens to be that the whole bottom is a number, then how do I say this a better way? If this bottom middle is a number, then the entirety of the bottom must be encompassed by that, or must be a part of that number, right? So because this is a 5, all of this must be part of the number. If this was like a 1, for example, the number would be 351. You'd never get a case where this was something and then where this was a number and then either of those were also numbers. They'd all be part of the same number. So you just have to do that check first. And so that's what my adjacent numbers function looks like. So really quick, what I do is I have this number function that says, I want to see if my current position is a number, and if it is a number, what is that number? And so I use the option here to signify, is it a number? And if it is, what is that number? And basically what I do is I say, hey, if that value is a digit, I'm going to move to the left as far as I can, and then I'm going to return that whole number. So the idea is if I'm at the 5 here, I'll move all the way to the left to get this, and then I'll include that whole thing. And the idea is, it's probably makes more sense if you look at it up here. As I'm going through this adjacency list, eventually I hit a 7. I want to move all the way to the left and then make that my whole number and say, hey, there is a number right here, and it happens to be 467. So what that allows me to do is I can just check the left side, see if it's a number, and if it is, I add it to my result list. Then I can check the right side, and if it's a number, I add it to my list. And then here's the gotcha block for here. I'm doing the top here. Is I say, hey, if the very top middle digit is a number, then the whole thing must be contained in it. So I only just need to check that position for a number. Otherwise, I need to check the top left and I need to check the top right. But all of these are the same if let some n number blah, and I just do different positions, right? Different adjacencies to it. Oh, I should say, I think I said I used the adjacency list. I ended up not doing that because I couldn't find a good way to like differentiate in this case, right? I didn't want to have a weird case where I found a number here and a number here, but they actually are the same number because they're this number right here. So you have to check this one first to get it, at least in the way that I implemented it. Okay, so once I've done the top, and then I just do the bottom as well, and it's literally the same thing, but instead of x minus 1, I'm now doing x plus 1. Okay, so what does that all look like then? Like, it looks like it's a lot of copy paste. I think I could probably clean that up a little bit more, but the idea is just check each place and see if it has a number, and if it does, add that to the list and return it. And then the solution then is as simple as saying what I showed you up here, I think earlier. Show me all the adjacent numbers. If the count is exactly 2, then multiply them together and add them to my sum, and that gives me the solution. So I'll run this again. And these were the results I got. I should say, I don't know if you guys are following along with me, but you may not get the same answers I do. Like, you can't just plug these numbers in to get to your solution because the inputs are different. I don't know how many there are, but I gather that there's multiple different inputs, and you will get a random one of those inputs based on, your account. And so you may not get these same numbers, but these were the numbers I got that solved it for me. Okay, so that was day 3. Again, I did not get to the Haskell part. I obviously I want to keep doing this stuff because I think it's fun. I think I want to keep up with the days though. We'll see how long that happens. I may eventually get to the point where I just don't. Especially now that I've had the last few days off. I'm going to be going back to work for a couple days, and then I have some family things this week. I may only implement it in Rust, and I'll try not to do this like, here's my solution, but I may have to do those a couple days. But I do just want to show you, here was my solution, here's how I did it in Rust. And if I ever do get to it in Haskell, I'll do a video, show you how I did it. Or maybe I think I can finally do YouTube Live. Maybe I can start doing that, and you guys can help me solve it in Haskell. So I think this one will be a little bit harder in Haskell. I'm trying to reason about how you do it in your mind. I know if you have a list, you can use like the bang bang operator to like get a specific element. So maybe you can solve it in Haskell in this same way, or in I guess any functional language in the same way. You just use like the adjacency thing. That's not tough. It's these things right here where you're saying, go one position to the left or go one position to the right. That feels a little iffy when you're doing it in Haskell. I'll have to see maybe I'll just look and see how other people solved it, and we can talk about it. But anyway, there's my answer or my solution to it. It was a fun one. A lot of people had issues with bounds checking. I actually turned out not to be the case when I was looking at other people complaining about how hard it was. Obviously I do some bound checking here to make sure x is greater than 0 and x is less than 0. I guess though, if you don't use like the equivalent of the lines function here in Rust, right here, some programming languages include the new lines as you're doing this, and that caused some issues. Things like along those lines where if you're just not careful with the bounds checking, same thing with the saturating sub, you run into issues that you have to figure out. I actually think there are potential edge cases that I'm not accounting for in these checks. For example, y, if you call adjacent numbers on y equals 0, y minus 1 is you know, ungood. It's a that will cause that'll give you a stack trace for underflow or whatever it's called in Rust. Um, it would fail the bounds check. So I guess I don't do that here. I might have to do some. There are some edge cases that I don't check, so maybe my input just didn't have those same problems as those people had, and I didn't have to worry about those ones. So anyway, there you go. Hope you guys enjoyed it. As always, I'm looking for input. I've gotten a couple comments about trying to keep the stuff bigger. I'm always trying to improve that stuff. I'll keep doing it in Rust as much as I can. It's the one that I feel like I'm comfortable enough with that I can solve most of the problems, and I really enjoy programming in Rust. But I also I want to go back to my like functional roots. So again, I'll try and do it in Haskell as I can. Anyway, um, send me your solutions. I'd love to see what you got down in the comments. And I'm always looking for ways to improve. Let me know what you'd like to see. If you want me to like look over your solution, yeah, go ahead and send it to me, and maybe we could do some videos where we see how other people solved it and the pros and cons of doing it one way versus the other way. We'll talk to you guys later.